In 1913, famed science fiction writer H.G. Wells published a book in serialized form titled A Prophetic Trilogy. A year later, the book was released in completed form with a new ending and a new name, A World Set Free. The novel, dedicated to Frederick Saude's work, An Interpretation of Radium, begins with the words, "The history of mankind is the history of the attainment of external power. Man is the tool-using, fire-making animal, always down a lengthening record, save for a setback ever and again, he is doing more." In the book, Wells tells of the outbreak of a continent-wide war between the Allies and the Central Powers, wherein the narrator describes a new weapon, developed from the knowledge learned by Saude, William Ramsay, and Ernest Rutherford about radioactive decay. In the novel, Wells writes of an airplane pilot and companion on the way to deliver their deadly payload to the capital of Germany. Quote, "The face of the adventurer at the steering wheel, darkly visible ever and again by the oval, greenish glow of the compass face, had something of that firm beauty which all concentrated purpose gives, and something of the happiness of an idiot child that has at last got a hold of the matches." His companion, a less imaginative type, sat with his legs spread wide over the long, coffin-shaped box, which contained in its compartments the 3 atomic bombs, the new bombs that would continue to explode indefinitely, and which no one so far had ever seen in action. Hitherto, carolinum, their essential substance, had been tested only in almost infinitesimal quantities within steel chambers embedded in lead. Beyond the thought of great destruction slumbering in the black spheres between his legs, and a keen resolve to follow out very exactly the instructions that had been given him, the man's mind was a blank. His aquiline profile against the starlight expressed nothing but a profound gloom." Unquote. Wells describes this new type of bomb in the following way in the book. Quote, "Never before in the history of warfare had there been a continuing explosive. Indeed, up to the middle of the 20th century, the only explosives known were combustibles whose explosiveness was due entirely to their instantaneousness. And these atomic bombs which science burst upon the world that night were strange even to the men who used them. Those used by the Allies were lumps of pure carolinum, painted on the outside with unoxidized cytonator inductive enclosed hermetically in a case of membranium. A little celluloid stud between the handles, by which the bomb was lifted, was arranged so as to be easily torn off and admit air to the inductive, which at once became active and set up radioactivity in the outer layer of the carolinum sphere. This liberated fresh inductive, and so, in a few minutes, the whole bomb was a blazing, continual explosion. The Central European bombs were the same, except that they were larger and had more complicated arrangement for animating the inductive. Always before in the development of warfare, the shells and rockets fired had been but momentarily explosive. They had gone off in an instant, once for all, and if there was nothing living or valuable within the reach of the concussion and the flying fragments, then they were spent and over. But carolinum, which belonged to the beta group of Hyslop's so-called suspended degenerator elements, once its degenerative processes had been induced, continued a furious radiation of energy, and nothing could arrest it. Of all Hyslop's artificial elements, carolinum was the most heavily stored with energy and the most dangerous to make and handle." Unquote. Written just a year before the first of the great European wars of the 20th century, Wells' prediction was ridiculed by most scientists of the time, who viewed liberating the energy of the nucleus of the atom as little more than the fantasy of the great science fiction writer, a plot device that, like so often in the case of good science fiction, is used to explore the social ramifications of the use of new technology. Coming on the heels of that book's publication, that war, fought with conventional explosives that wreaked havoc and destruction unimagined just a few years earlier, changed the landscape of Europe, both physically and politically. Yet it was a war wherein the weapons were understood to be merely more lethal iterations of Alfred Nobel's original inventions. The ideal that scientists would be able to harness the enormous energy of radioactivity was thought to be so far out of reach of human capacity that it was considered little more than a way for a writer to justify the formation of a world government in a work of fiction. However, by 1933, the unthinkable was no longer the toy of a science fiction writer. In that year, the physicist Leo Szilard would use the term atomic bomb in a scientific paper for the first time, in direct reference to Wells' book, and in 1934, he would copyright it. By 1938, a woman in exile in Sweden would take data being produced in Berlin and show that not only could the nucleus of the atom be split, but that humans could do it in a way that could be controlled and sustained. Just 7 years later, something startlingly similar to Wells' fiction was exploded over Hiroshima, Japan, ushering in a new and terrifying era. And while the development of the weapon did not catalyze the formation of a one-world government, it did help usher in the United Nations and lead to an arms race as predicted by Wells in the novel. In this podcast, we'll continue to trace the development of nuclear physics from the work of Fermi in Rome through the laboratories of the Kaiser Wilhelm Institute in Berlin to the desert of New Mexico, where Wells' fiction was made very, very real for the first time.
Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery.
Series 2, A History of the Atom. Episode 20, A Fission and Fascism. When we last boarded the Odyssey, our ship of discovery and exploration, we were discussing the work of Enrico Fermi and his team in Rome. For his work in quantum field theory as applied to the processes of the nucleus and the inducement of artificial radioactivity using neutron bombardment, Fermi had been given the nickname the Pope, as he seemed infallible. He had discovered the statistical rules for particles that obeyed the Pauli exclusion principle before Dirac had. He had rescued Pauli's neutrino from obscurity by showing that it was necessary to explain both types of beta decay. He had perfected neutron bombardment and had shown that it was possible to increase the probability for a neutron to be captured by a nucleus if the neutron was first slowed by a moderator. Moreover, he had claimed to have created the first transuranic elements, though, in this, his nickname would prove to be less accurate. Nevertheless, it was clear that for the first time since Volta had studied electricity and Marconi had worked on radio transmission and reception, there was great physics being done in Italy. Before we get into the meat of the story, I think there's one thing, however, that should be addressed as a backdrop for the events that are about to unfold. During the time of many of the discoveries we've been talking about, and that we will talk about, there's a sea change in political theory taking place on the European continent. With the ending of World War I, there is rampant dissatisfaction with the major governments who had gotten everyone into the war in the first place. While the monarchies of Germany, Austria-Hungary, and Russia had fallen, the democracies of England and France had not fared much better in the court of public opinion. In the eyes of those who had survived the war, the politicians a generation older had thrown them into a meat grinder for little reason beyond the Byzantine power politics of an old Europe that was corrupt. While communism offered one option to some, the failed socialist rebellions of 1918 and 1919 in several places in Central Europe led to the rise of another model, what is now known as fascism. Beginning in Italy in 1922, This, quote, revolution against revolutions, unquote, brought to power Benito Mussolini as prime minister in Italy after his organization staged the March on Rome. Hitler's failed Beerhall Putsch will model itself on this idea, and when Hitler comes to power a little bit later, it will in many ways be due to the success of the Fascii Party in Italy. The question that I had regarding all of this is why so many scientists agreed to work in fascist regimes that will be the cause of so much suffering over the course of the next 2 decades. To answer this, I turn to my colleague, Dr. Gary Cox, who is a historian specializing in the period of the 2 world wars in Europe. The point that he makes, and I think that should be emphasized, is that to understand the actions of those during this time, we have to work very hard to take ourselves out of the history that has been lived back to that time in 1923 and 24. Try to think of yourself as a citizen of Italy during that time. You've lost a generation of men due to having gotten into a war based on the promises made by what you see as a pair of corrupt democracies, England and France, who sold you out when the peace was made. A series of strikes and threatened revolutions from the socialists have made your life miserable. Then comes the strong man who says there's a better form of government. He says that the government can create a public-private partnerships that will keep the factories running and the materials and goods flowing. These partnerships will provide good jobs and wages for reasonable work hours for a lot of people. A safety net will be created out of taxes on the revenues so that the poor and elderly will have a chance to have a life with some dignity. The trains will run on time, the country will modernize, and everyone will benefit. And let's say, for the most part, that works. How do you think you'd feel about that? Now, this description isn't meant to minimize the other side of the coin. The slow, inexorable removal of a free press, the loss of a true electoral system that allows for more than one-party rule, the reality that if you don't like the package of wages and benefits the partnerships are offering you, you have little recourse but to protest, which will invariably lead to arrest and imprisonment. But when you've just faced chaos and lawlessness, you might just be willing to give up some of those freedoms to make sure there's bread on the table. More than that, what you need to sort of keep in mind is that you don't actually know that all the negative stuff is coming. We look back and can now see all of that, but in the mid-1920s, fascism is the new and exciting political idea. It seems modern and progressive at a time when the old systems have failed so badly. And when, in 1929, the excesses of the mostly unregulated American capitalism plunged the world into a depression, the world except Italy, that is, the one other model of political and economic cooperation is called into serious question. It is out of this failure that the collapse of the Weimar Republic in Germany takes place, and it's out of this failure that Hitler is able to become prime minister of Germany. In first Italy and then later in Germany, the ideas of fascism are initially embraced by society, including the scientific communities, because it seems to offer a modern and viable alternative to the apparent ineffectiveness of capitalistic democracy and the social chaos, class warfare, and violence of revolutionary communism. Of course, many of those who supported the fascist movements, or at least stayed for nationalistic reasons, would live to regret their decisions, as the leaders of those movements either veered towards autocracy or were madmen bent on genocide and domination. To bring this short digression to a close, I want to say that while this certainly is not to be anything more than the briefest of thumbnail sketches, and I'm sure one can find much more nuanced and much more complete discussions of these ideas in any number of other places, I hope that it will help you come to terms of why so much of the work being discussed in this episode takes place in countries that will soon be on the wrong side of history, by scientists who would have never agreed to or supported the actions of these regimes had they known what the future had held in store. Okay, so let's return to the scientific narrative. With the discovery of the neutron and the recognition that, like the proton, It was a fundamental particle of matter. There was obvious interest in trying to build a model of the nucleus that incorporated it. This model would have to be able to account for the nearly spherical shape of the nucleus and the fact that the nucleus seemed to have nearly constant density throughout its volume, constraints on the model that had been determined from Rutherford's scattering experiments. The model would also have to account for the accumulating data on bombardment by various particles such as the proton and the neutron experiments that had been done. The first attempt to move in this direction was taken by the Russian theorist George Gamow, with what is now known as the liquid drop model. Gamow's idea was to treat the nucleus of the atom in a classical rather than a quantum fashion, and work from the analogy of a drop of liquid that's able to hold itself together in a mostly spherical shape, but that can dynamically adjust to interactions with external perturbations. One of the most relevant ideas in the model is that it allowed for multiple forces to be considered in determining what was holding the nucleus together and what was trying to push it apart. Holding the nucleus together was a nuclear force and certain quantum mechanical interactions, while the electrostatic forces between the protons were trying to push it apart. A final force was what was called the surface tension term, that represented the idea that a nucleon at the surface of the nucleus interacted with fewer neighboring nucleons than one in the interior of the nucleus, and thus would be easier to eject during the interaction. In 1935, Niels Bohr and Charles Weisacker, a protege and close friend of Heisenberg's, refined the model into something that is usually referred to as the compound model of the nucleus. The big modification of Gamow's work was that the two used Yukawa's representation of the nuclear force to come up with what is known as the binding energy of the nucleus. This calculation was a representation of how much energy was stored in the nucleus as a result of the various forces and interactions between the constituent nucleons. What they determined were two things. First, they came up with a curve of the binding energies for various elements and their isotopes. The curve is really interesting because it has a U-shape with higher values at the low end of the number of nucleons and at the high end as well. The minimum of the binding energy was somewhere around the element iron, which has an atomic number of 26, and a total number of protons and neutrons of around 55. I'd like you to put this idea on the back burner for a little bit because it's going to become very important to our story a few years down the road. The other thing they came up with was a way of dealing with what happened to the nucleus statistically when it was bombarded with a proton or neutron or alpha particle, for example. The model said that if you could think of the nucleus as having a certain sort of temperature, a certain amount of jostling around of the nucleons. When you shot a particle into a nucleus, it would be absorbed and its energy would be incorporated into a new compound nucleus. This energy would effectively raise the temperature of the nucleus. Now, if this temperature was still lower than the binding energy in a sense, the new nucleus would be stable for a time. While a neutron or a proton might undergo beta decay, or anti-beta decay in the case of a proton, the number of nucleons would stay the same and you'd end up with a more massive nucleus, which meant you'd either created a new element if the end result was adding a proton, or you'd created a new isotope of that same element if you'd ended up adding a neutron. However, if the energy given to the nucleus was too great, it would boil a particle off of the surface of the nucleus. Sometimes this would be a proton, sometimes it might be a whole alpha particle. With the escape of this particle, the temperature of the nucleus would be lowered and it would become stable again. A physical analogy for this might be to think of a big bucket filled with ping pong balls. In the bottom of the bucket, think of some sort of an agitator that sort of gets the balls bouncing around in the bucket. The amount of bouncing the balls undergo is a bit like the temperature idea we've been talking about for this compound nucleus. Now let's say that the agitator is set pretty low or that the walls of the bucket are pretty high so that the ping pong balls don't ever bounce up high enough to be able to get out of the bucket. If we shoot another ping pong ball in, it won't add enough to the jostling for that to change. But if the wall of the bucket is lower or if there's more agitation, then if we shoot in an extra ball, it might interact and give another ping pong ball enough energy to jump out of the bucket. It turned out that the height of the wall of our analogy bucket had to do with that binding energy that we've been talking about. And we'll have more to say about that in a minute. This type of model was exactly the kind of thing Bohr would come up with, as his forte was creating a sort of quantum classical hybrid type of model that allowed for calculation even if the classical representations of the various processes were a bit suspect. The important thing is that this model, based both in high theory and empirical data, much as the old quantum model had been, allowed for a variety of calculations to be done that would guide various nuclear physicists and chemists in creating new radioactive isotopes of various elements, something rather useful in the field of medical physics as we've discussed in the previous episode. Now, to go forward, we have to go back a ways and pick up a thread that we have up to this point completely neglected. And that's the work of a colleague of J.J. Thomson's named Francis Aston. One of the things that Thomson had done as part of his cathode ray research was to extend his use of using magnetic fields to measure the charge-to-mass ratio of the cathode rays to building the very first, very crude mass spectrometer. You're probably very familiar, or somewhat familiar anyway, with the term mass spectrometer from watching one of the many forensic crime analysis shows on TV. In these, a sample is fed into a machine which does some sort of magic and produces a sheet of data that a tech then helps the main scientist character interpret that provides a key piece of evidence for solving the case. While much of this is true, it ignores all the details of how the actual machine works. So let's take a moment to talk about that. The way the mass specs works is that it takes a sample and vaporizes it into either atoms or molecules. It then strips an electron off of each atom or molecule of the sample so that they have a single positive charge in a process called ionization. The ionized molecules are then accelerated using an electric field to a specific velocity using a very clever but only tangentially related bit of apparatus known as a velocity selector. Now's where the important thing happens. These atoms or molecules are then shot into a chamber with a constant magnetic field. As I mentioned in the previous episode on Lorenz's cyclotron, magnetic fields have the ability to bend the paths of moving charged particles. While the radius of the circle of the particle will travel in depends on the velocity, something that's the same for all of the particles in this application, it also depends on the mass of the particle, which is what Thomson had used to determine the charge-to-mass ratio of the cathode ray. Still with me? I hope so. In our mass spec, the sample we fed in was made up of a bunch of different things, maybe hydrogen and nitrogen, carbon and oxygen if it's some sort of organic compound. Now, since each of these atoms have a different mass, they'll travel in a semicircle of different radius before striking a detector. The more mass the atom has, the bigger the radius. What the detectors do is count up the number of atoms or molecules in the sample and compare the ratio. If there are 2 times as many hydrogen atoms as there are oxygen atoms, then the sample probably had water in it. Now, this example, of course, is a really simple one, and the actual process of analysis is a lot more complex, but hopefully you get the picture. So, Thomson's original mass spectrometer is way too crude to be able to get the kind of accuracy needed to do this sort of analysis, but Aston was able to develop and build on this work. Aston's original goal was to do isotope analysis, and by 1912 he had achieved the sensitivity to be able to tell 2 isotopes of neon apart, and to accurately determine the difference in their atomic masses. During World War I, Aston worked on aircraft research, and in 1919, with the war ended, he returned to developing even more sensitive mass spectrometers. Over his career, Aston would discover over 200 new isotopes of various elements, work for which he would be awarded a Nobel Prize in Chemistry in 1922. More importantly for our discussion, and sorry for having to build the arc a bit here to get to this point, he discovered a really, really interesting thing. He found something that was called the Mass Defect. When he used his mass spec to indirectly measure the mass of the atoms of his samples, he always found that the mass came out just a little low. For example, if you took an atom like carbon-12, you could predict what its atomic mass would be by adding together the mass of 12 single protons. Now remember, at this point the neutron hasn't been discovered yet, though when it was found to have a mass that was nearly identical to the proton. And the electron is so much less massive than the proton it can mostly be ignored for this analysis. When Aston measured the actual mass of the carbon atom, though, he found that its mass was just a little bit less than it should have been if you just counted up 12 protons. What he found was that this was true for every single element and isotope of an element that he measured. He concluded that bringing together of the protons to form the nucleus caused some of the mass of those protons to be lost. So where did this mass go since the mass had to be conserved? Well, what Einstein had shown was that mass could be converted into energy using that very, very famous E equals mc squared expression. Gamow was the first to hypothesize, and Weisacker was the first to actually calculate that the lost mass was what created the binding energy of the nucleus. When Cockcroft and Walton, and I apologize for getting Walton's name wrong in the last episode, when they were using high-energy protons to split the lithium nucleus, they were able to confirm that the mass defect was in fact converted into the binding energy of the atoms. It was at this point that Zillard was able to make his prophetic prediction about the possibility of a chain reaction. He said that if some sort of nuclear process produced neutrons, and those neutrons interacted with other atoms to produce that same process, there could be a multiplier effect. If that process were to release some of the binding energy stored in the nucleus, that chain reaction process could generate an awful lot of energy in a fairly short period of time. In 1932 and 33, it was thought unlikely that such a thing would happen. But as Fermi's team learned how to do neutron bombardment and then how to increase the capture efficiency by slowing the neutrons down with a moderator, the physics and chemistry communities began to inch closer and closer to realizing Zillard's prediction. Zillard himself will have a very important role to play in this down the road a few years. As I mentioned earlier, the first person to dimly glimpse the real possibility of fission was Ida Noddack. Noddack and her husband Walter were well-regarded chemists who had discovered the element of rhenium and possibly, though there's a lot of debate about this, technetium. In looking at Fermi's data, she suggested that the chemical analysis his group had done that proposed to have isolated element 93 from the original uranium, element 92, sample, through chemical reaction, would also have shown a positive indication if instead of adding a single particle to the uranium nucleus, the neutron had split the nucleus into two or more lighter nuclei that would also have chemically reacted with the indicator. Noddack suggested that Fermi should have checked for the presence of those elements to exclude them as possible products of neutron bombardment. While Noddack's criticism and ideas were eventually shown to be accurate, it should be noted that she offered no discussion of the energetics of how such a splitting up of the atom would work. In light of this, the broad scientific community tended to view her paper as, in the words of Otto Frisch at the time, carping criticism. While some are quick to suggest that this reaction is an example of the pervasive gender bias in European physical science community at the time, something clearly shown in the case of Lise Meitner, as we'll shortly discuss, I tend to see this as something much more complex. Yes, perhaps there is a measure of sexism here. But more than that, what I think we see here is the power of scientific reputation. While Noddack was a reasonably well-regarded scientist in her field, Fermi was the Pope. He had been so right, so often, in so many fundamental ways, that when he went back in response to Noddack's criticism and improved his method of chemical analysis and got results that confirmed his initial work, her suggestion to run a different set of chemical analysis tests was broadly ignored, at least initially. Scientific reputation, I think, is one of the hardest biases to overcome in science. While the validity of an idea in science is supposed to rest on the empirical evidence provided to support it, something Fermi certainly had in part, but not completely, it's really hard not to let the reputation of someone who has been really successful in a field sway the thinking of the community of research. What Fermi should have done is run a series of chemical analysis that would have either falsified Noddick's hypothesis or his own. Instead, probably convinced that this process worked exactly the same way so many others had, Fermi only tested his own idea. This is a case where we see the value and utility of Karl Popper's criterion of falsifiability. Fortunately, at least when considering the purpose of scientific discovery in this case, science has this process of self-checking and self-correction built in, and it would be this process that would, in 1938, expose Fermi's error. To understand this, we should take a few minutes to talk about the interaction between chemistry and physics in this area and look at the place where that interaction was most productively realized, the Kaiser Wilhelm Institute in Berlin. At this time, the boundaries between nuclear physics and nuclear chemistry were pretty blurry in some regards. Broadly speaking, the work of understanding the processes taking place in the nucleus of the atom was considered physics, while the analysis of the products of nuclear processes and their reactivity, physical attributes, and characteristics was generally found in the realm of nuclear chemistry. However, as should be clear, the two fields had a great deal of overlap, with the chemists using the semi-empirical models of the physicists, and the physicists doing some of the classification of isotopes using various separation techniques, including the magnetic methods we discussed earlier. Nowhere was this collaboration better exemplified than with Otto Hahn and Lise Meitner in Berlin in the 1920s and 1930s. As Meitner's full biography is something I'd like to cover in a supplemental, let me just make a few remarks here to set up the science. Meitner was an experimental physicist with strong mathematical talents, who had overcome a series of significant obstacles to earn her PhD and take up studying radioactivity in Berlin in 1906. Her work attracted the attention of the director of the Chemical Institute there, and he put her in contact with a very good chemist who had made the seemingly career-killing move of deciding to study radioactive chemistry in the tradition of Soddy, one Otto Hahn. The two found that they worked tremendously well together and began a collaboration that would last for 30 years. Meitner's knowledge and skills as a physicist were very complementary to Hahn's skills as a chemist, and they were able to make remarkable progress in their joint fields. In 1938, however, that all changed. Meitner was an Austrian Jew with citizenship in a country outside of Germany, and as such, she was shielded from losing her position when Hitler's Nazi Party instituted the civil service laws in 1933, as they only applied to German citizens. However, once Germany took over Austria in an event known as the Anschluss, Meitner's Austrian passport ceased to be valid, and she became something of a German citizen. Learning that she was going to be removed from her position at the Kaiser Wilhelm Institute, she applied for a passport to Denmark to work with Bohr, only to have that denied. When she found out that she was to be arrested and taken to a concentration camp, she fled to Denmark under the cover of darkness with little more than Otto Hahn's grandmother's wedding ring in her possession to bribe a border guard if necessary. Once she got to Denmark, she flew to Copenhagen where Bohr arranged for her to travel to Sweden. While she was there, her colleague Hahn, along with a student named Strassmann, found something very odd. The two had been doing neutron bombardment experiments, very much in the vein of Fermi's group, in order to determine the radioactive decay chain of the transuranic element everyone thought was being produced as it transmitted back down to radium. What they found instead was that there was barium in the sample after it had been bombardment. At first, they thought they must have made a mistake with their chemistry, but after double and triple checking their work, Hahn and Strassmann concluded that the barium was really there as a decay product of the neutron reaction when it shouldn't be. Just a few months earlier, What Hahn would have done was walk down the hall to Meitner's lab and said, "Hey, would you mind looking this over?" We seem to have come up with something really very unexpected. Now, however, Hahn had to send a letter to Sweden attempting to explain what he was doing, and Meitner had to try to understand the work without looking at the apparatus or all of the data directly. Moreover, as she was a refugee without an academic institution to work at, she couldn't actually replicate Hahn's work. Over Christmas of that year, Meitner's nephew, also a physicist who was working with Niels Bohr at the time, came to visit Meitner. His name was Otto Frisch. As the two took a walk, they began to discuss what might be going on in Hahn's work, and Meitner had the idea that perhaps the uranium nucleus actually had split into two much smaller pieces. Upon returning home, Meitner worked up the energetics of the nuclear reaction using the liquid drop model and found that she could explain Hahn's results very well. Moreover, her calculations suggested that in addition to the two smaller nuclei being produced, there might be 2 or 3 neutrons shot out of the reaction. She and Frisch then worked out a paper communicating these results via a series of telephone conversations between Copenhagen to where Frisch had returned following his holiday in Sweden. As the paper neared its completed form, Frisch shared the work with Bohr, who was immediately taken with what they had done. His response, in fact, to the paper was, quote, "Oh, what idiots we have all been. Oh, this is wonderful. This is just as it must be," unquote. With this encouragement, Frisch was able to confirm Meitner's calculations, including the possibility of neutron emission in his lab in Copenhagen. The two published a paper detailing the theoretical and empirical results that electrified the physics community around the world. It was here that Frisch first coined the term nuclear fission in a direct reference to the biological process of cell fission. Additionally, Meitner had done the binding energy calculation of the reaction and found that the binding energies of the reaction products were significantly less than the binding energy of the original uranium nucleus. This difference in the before and after energies of the nuclei would be released as an energy of motion for the particles, including any possibly emitted neutrons, as well as the emission of a high-energy photon. And this is all, of course, going to be of great importance down the road. In France, just prior to the publication of the paper, the Zillard Curies had independently discovered Hahn's and Strassmann's results. When the paper from Meitner and Frisch was communicated to Bohr, who, by the way, had traveled in this time to America to begin a sabbatical working with Einstein at Princeton, he quickly communicated it to a number of scientists working in the United States, who almost immediately replicated the results. One of these groups, working with a huge cyclotron at Columbia University in New York, was headed by none other than Enrico Fermi. So how did Fermi get from Rome to Colombia? Over the course of the mid-1930s, fascism in Italy had really taken a turn towards oppression. Though it had once been admired as a solution to the ills that plagued society following World War I, its system of one-party rule and repression of dissenting points of view had become very pronounced at the time. As Hitler and Mussolini grew closer in their collaboration, the Italian version of fascism began to adopt some of the same ideological strains of the Nazi Party, including its racial views. When, in 1938, Mussolini's government adopted civil service laws similar to those Hitler had enacted in Germany in 1933, Fermi, whose wife Laura was Jewish, had had enough. When the two traveled to Sweden on the occasion of Enrico being awarded the 1938 Nobel Prize in Physics for work that Hahn and Meitner were just about to disprove, the Fermis took the opportunity to defect and move to New York, where Enrico took a position that had been offered to him by Colombia. Within just a month or two, Fermi was working with the big science machines at Colombia, including the cyclotron there, to reproduce and extend the work of Hahn and Meitner. Before I move on from here, I'd like to stop and just for a moment consider this one piece of history in the story. As we'll discuss in the next episode, it will be Fermi, working under the direction of the U.S. Army's, or actually U.S. military's, Manhattan Project, who will create the first self-sustaining fission reactor under the bleachers at the University of Chicago in an old squash court. This piece of work eluded Germany's nuclear physicists, including Heisenberg and Weisacker, for the entire duration of the Second World War, even as they struggled to do that very thing that Fermi was going to do. Now let's say that Mussolini hadn't enacted the racial laws of the Nazis. Would Fermi have stayed in Italy, as so many German physicists had done in Germany? Would he have been drafted to work on the Axis powers' efforts to construct a nuclear energy source? I don't know the answer to that question, of course, but I'm not sure that the autocratic or totalitarian tactics of the Italian Fascist Party wouldn't have been enough to make him flee. And while I think that it is likely that the Allied project would certainly have succeeded in producing the Fat Boy bomb that was eventually dropped over Hiroshima, it's not far outside the realm of possibility that without Fermi's help and direction, the reactors to produce the plutonium that powered the Trinity and Little Man weapons might never have been built. Moreover, one kind of has to wonder if the German project would have been much more successful had Fermi been actually more useful in moving the operation led by Heisenberg in the correct direction. To return to our narrative, one of the things that Fermi got to thinking about was what happened to those neutrons that had been produced in the first splitting of the uranium nucleus. He wondered if they might interact with other uranium nuclei, get absorbed, and induce them to split. If this were true, wouldn't that produce the exact type of chain reaction Zillard had predicted just 7 years earlier? And, if that was the case, why hadn't that happened in his experiments back in Rome or in the German, French, or American experiments of the last year? At the American Physical Society meeting in January of 1939, Bohr and a former student, John Archibald Wheeler, who was, by the way, was now the president of Princeton, advanced an explanation to this question. If the most common isotope of uranium, known as uranium-238 due to the number of protons and neutrons in the nucleus, had done the absorbing, a chain reaction should have started. However, what had actually absorbed the neutron and undergone fission was a uranium-235 isotope atom. What they showed was that while an atom of uranium-238 could absorb a neutron and change into something else, it could not actually undergo fission. So let's kind of expand on this a little bit. What these guys are saying is, if one were to pick up a chunk of pure uranium, what one would find was about 99% of the sample would be this stuff called uranium-238, and only about 1% or so of it would be this uranium-235. Thus, the uranium-238 tended to absorb most of the fast neutrons without undergoing fission, and that meant that it acted like a damper to any sort of chain reaction. Moreover, since most of the emitted neutrons were moving really fast, there was a pretty low chance of any of them being absorbed by the atom of uranium-235. It was only Fermi's slow neutrons that actually seemed to be able to cause fission in the uranium-235 atoms, actually. Bohr and Wheeler claimed, though, that if you could get a large enough sample of uranium-235 and you could moderate the speed of the emitted neutrons from an initial reaction, you could produce a self-sustaining reaction that would release a lot of energy. If this were done in a controlled fashion, the energy could be captured and used to heat water and spin a turbine to produce electrical power. If, on the other hand, the reaction were allowed to grow unchecked, the energy would be released catastrophically. In March of 1940, Alfred O. Neer of the University of Minnesota managed to isolate a 0.2 gram sample of uranium-235, and through neutron bombardment, show Bohr and Wheeler's conjecture to be correct. Neer had used Aston's mass spectrometer design to build the apparatus that allowed for the laborious separation of the very tiny amount of the uranium-235 isotope. As all of this was unfolding, there were several very interested parties watching the developments. As I discussed in the episodes related to Heisenberg, the German military wondered if the technology could be developed either to produce a powerful power source or, perhaps, a weapon. Another interested party, of course, was Leo Szilard. Zillard had fled the Nazis in Europe and had immigrated to the United States, where he had landed at Colombia. Upon reading the various scientific papers related to working nuclear processes in late 1938 and early 1939, he became very concerned about this possibility that the German military would be able to weaponize this whole process. After conversations with Eugene Wigner of Princeton and Alexander Sachs, it was decided that something must be done to encourage the United States to undertake a similar project. In October of 1939, just days after Germany invaded Poland, Sachs delivered a letter signed by Einstein to President Franklin Delano Roosevelt. The letter read, in part, quote, "In the course of the last 4 months, it has been made probable through the work of Zillard in France, as well as Fermi and Zillard in America, that it may become possible to set up a nuclear chain reaction in a large mass of uranium, by which vast amounts of power and large quantities of new radium-like elements could be generated. Now it appears this could be achieved in the immediate future. This new phenomena would also lead to the construction of bombs, and it is conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type, carried by a boat and exploded in a port, might very well destroy the whole port, together with some of the surrounding territory. However, such bombs might very well prove to be too heavy for transportation by air." Unquote. It is likely that this letter catalyzed President Roosevelt to set up a working group to study the feasibility of such a project, and to take the first steps to determine what would need to be done. It is at this point we'll pick up our narrative in an episode I'll probably titled The Dawning of a New Age later on down the road. Between now and then, however, I'd like to produce a supplemental episode on Enrico Fermi that will also take a look at the Italian fascist movement in a little more detail, and fascism in general. As always, thanks for listening, and if you've got comments for the show, you can post them to the website, thescientificodyssey.typepad.com, or on our Facebook page. I'd sure appreciate it if you could take a moment to leave a review of the podcast on whatever service you use to listen to us with. There are about 150 people who regularly listen, and if just 1 in 5 were to head out and let folks know through the giving of a few stars in a review at places like iTunes and Stitcher, that would move the show up in the rankings, which would really help us get the word out about what we're doing. One more thing. I think we need a name for those of you who follow the podcast. While we're all on the crew of the Odyssey, of course, there needs to be something more, hip or something. The lovely wife suggests that I call you all the Lab Coats, or the Lab Coat Posse, or something like that. I kind of like the sound of it, but I'd sure like to know what you think. So even if you don't leave us a review, drop us a note at the Facebook page and let us know if that's a good title or if you have some other good idea. I think it'd be really cool if we get some sort of a name or identity that we can all go by. Anyway, that'll wrap it up for this week. So until next time, full sails on your journey.